I have to confess that after attending this conference, I am ashamed that I have to give a talk which is called Panorama Talk, since in my view, essentially every participant of this conference has more panoramic views than I do. So you can consider this as a panoramic view through a keyhole. So first of all, what I want to cover to add insult to injury, I will start from elementary school, although it would be unnecessary in this audience. So I mentioned the case of constant coefficient or equations. Then I shift to periodic operators. And then I will discuss essentially analytic rather than topological analytic properties of dispersion relations and Fermi surfaces. Many of those would seem to be very esoteric, but they turn out to be significant to understanding some of the spectral and physical features. There is a long list of distinguished people who have contributed this information, so I have no way to include all the references or essentially any references here. You can look at my survey and Bulletin of American Math Society in 2016, where there is extensive reference list, and those things I referred to. There are some more recent papers that might not be covered there, and I just list some authors like Charles Pfefferman, Mike Weinstein, Filonov and Konchkovsky, brilliant recent papers in discrete and tight binding case by Vinsai Liu, Stephen Shipman, and Bikralaika, Kanzani and Cox, Marzola, and our paper also. Okay, so this is essentially the table of content. Now let us start with, as I say, elementary school. I just want to dispersion relation and Bloch variety to and Fermi surface to appear naturally. Let's say we are in d-dimensional space. I will use the usual in mathematics notations. D capital is 1 over I times gradient. And you have operator L of D, which is just polynomial in D. For instance, minus Laplacian would be D squared. And it acts on functions. I will not specify now the classes of functions, it's irrelevant. Function u of x goes to this differential operator applied to it. After Fourier transform from u of x to u hat of dual variable, the operator becomes just operator of multiplication by a polynomial L of xi. You replace the D operator with xi. This is from elementary school, and this polynomial L of xi is called symbol of the operator. But you can take a high level, maybe too high level here view. This actually, oh, I missed some letters here. L is direct. You can think that this is L is represented as direct integral of those L of xi. You have L2 functions of xi, and you multiply by this symbol. This is the simplest case of direct decomposition. And let's consider the graph of this symbol. I call it B, and this is quote-unquote dispersion relation or Bloch variety analog for constant coefficient case. Not periodic, but completely constant coefficient. I put in quotation marks since no one says these words, but you will just see that it naturally leads to periodic case. And if you fix a value lambda, then the level surfaces, you can call it Fermi surface at the energy level. Both those surfaces are algebraic. clearly, since L of psi is polynomial. So they are given by polynomial equations. Now, let's get a little bit closer to periodic case. L will be now not a scalar operator, but matrix of differential operators, a system. Then L of psi will be a matrix. And this decomposition via Fourier transform still holds. But now what would we call this dispersion relation, quote unquote? The problem is that L of psi is now not a scalar. You cannot graph it. It takes values in matrices. So then we kind of simplify our life. And instead of considering L of psi, we only consider the spectrum of L of psi. So we can call this dispersion relation, quote unquote, defined as follows. Consider psi's and lambda such that lambda is in the spectrum of L of psi. In other words, it's given by the equation determinant equal to 0. Now it is the graph, but a multi-valued function, since the spectrum of L of psi consists of several eigenvalues, and those eigenvalues can collide, so it wouldn't be as nice smooth surface like in scalar case, but still it is a graph, but now of multiple valued function. Okay, I will mention later. And as before, Fermi surface is a level surface of this thing. Again, both of those sets are algebraic in the following sense that there is an algebraic equation that gives it. Here is the equation determinant of psi minus lambda equals 0. And since this is polynomially dependent on parameter matrix, determinant is a polynomial. However, it's important to mention that some information going from the full symbol L of psi to only the spectrum is lost, since you can easily cook up matrices that produce the same spectra without being the same. And in particular, later on, some topological features that are important in periodic case might be lost if you just look at the dispersion relation instead of the whole symbol L of psi. Now we are ready to go to constant coefficient periodic case. So in constant coefficient case, we had a group gamma, which was the whole space acting on itself by shifts, by translations. And this action was transitive, namely that there was one single orbit that covered the whole space. And what was L of psi? It was restriction of our operator to one-dimensional space generated by this exponent. And what is a space? Those exponents are actually all irreducible representations of this group. It's well known. So essentially, you expand, Fourier transform expands into irreducible representations of this group gamma and restricts to the corresponding spaces. Now, naturally, if you have not the full group RD, but a lattice, let's say after change of variables, I will assume that it's just integer lattice, which also acts by shifts, but now at non-transitively. Irreducible representations of gamma look essentially the same as here. Instead of psi, I will use letter k, since this will be what is called in physics quasimomentum or crystal momentum. There is one new thing, since that every this representation enters many times in our space, since there are many orbits. It's not the single orbit carrying the whole space. And this leads to the fact that this quasi-momentum is not uniquely determined. It's determined only modulo what is called the dual lattice, which in this case is just 2 pi times integer lattice. Since when you shift by it, nothing changes. By the way, now I want to emphasize that we will allow quasimomentum to be not only necessarily real, but also complex. And also, sometimes you might think it's esoteric, but a lot of information is hidden in exactly in complex domain. So now what is the eigenspace corresponding to this irreducible representation? It consists of so-called Bloch functions. We all know this notion. They are gamma periodic function times this exponential. And we get the famous direct integral decomposition of our operator L into our operator L of k. What is L of k? You restrict your operator L to the subspace hk, to the subspace of Bloch function with given quasimomentum. Again, integral is actually, it's R2, it should be RD, dimension D. Integral now is not over RD, but over the torus. You have to quotient out this dual group. Here, a couple of comments. That sometimes it is better to introduce a different variable, which is not frequently done in physics, as far as I understand, but it's in some cases it's more useful than quasimomental variable. You just I will call it Bloch multiplier, since this is what it is called in 1D. It is vector of e to the power I components of quasimomentum. So now this is a complex d-dimensional vector whose entries cannot be zeros. So this is punctured complex plane to the power d. If k is real, then this thing belongs to unit torus in this space, and that's exactly that Brillouin torus. So we quotient, go into Bloch multiplier, you quotient out this periodicity of quasimomentum, especially in discrete cases, as we will see, it's important since it produces algebraicity instead of analyticity. Now, what are the setups I want to consider? Continuous. In continuous case, let's say we have a periodic self-adjoint scalar elliptic operator of second order. There are some issues with operators of higher order. I will not address them here. If there will be question, I can tell. Ellipticity, or at least hyperellipticity, like heat equation, is important in the whole this study. All this analytic picture breaks down without it. Canonical example, you can think standard Schrödinger operator with periodic electric potential. Although, for instance, in photonic crystals, you need to deal with periodic Maxwell operators, which is much more complicated. Using tight binding model, for instance, the one very frequently used for studying graphene, you have a discrete operator. This is the graph of a graphene, this fundamental domain. It contains only 2 atoms per fundamental domain, and therefore those spaces are finite dimensional. In the case of graphene, they are 2-dimensional. So luckily, those L of k are matrices. Right away, I want to mention an important difference between continuous second-order operators and operators of higher order or discrete operators. Namely, second-order elliptic operators, they have uniqueness of continuation. So if you have the solution eigenfunctions that vanishes at any small ball, it is 0. It's not true in discrete case, and it's not true for higher order operators, like for elasticity, for instance. So this creates some problems which I will not mention here. And so now we have those Bloch and Fermi varieties. So namely, your operator L of k is just has this symbol shifted by quasimomentum, and it acts now on torus, so it has discrete spectrum. And as before, this is Bloch variety of or dispersion relation, and this is Fermi surface. Now, they are not algebraic anymore, but they still have an important analytic structure. Now, namely, they are analytic sets, even in complex domain, which means that there is an analytic function whose zeros give you those. Moreover, and it's turned out to be important in some cases, that there is an entire function of finite exponential order whose zeros give you those. In constant coefficient case, you know that this D is just, you take your symbol, graph of the symbol, and shift it periodically by dual-edge. So these are cartoons. For instance, this could be a dispersion relation. This is a particular case of discrete operator. And this, you take level set, it's Fermi surface. Certainly Fermi surfaces are much richer than that. For instance, this is Fermi surface of lead, and this is a sculpture of non-sculpture which actually replicates this. There are some very well-known things. For instance, how do you recover spectrum? Spectrum is just the range of this multiple valued function that gives you Bloch variety, or projection on lambda axis. And therefore, spectral gap edges occur where dispersion relation has extreme. Now, I will probably not dwell on this much, but essentially, and it's related to semi-classics, that if you have a narrow packet of Bloch waves, wave packet of Bloch waves, that essentially it behaves like it is under the rule of a constant coefficient differential operator whose symbol is the piece of dispersion relation near this, you can say the germ, near this point. For instance, near a non-degenerate but parabolic maximum of dispersion relation, particles will feel like they are in the free space, since parabolic looks like for Laplacian, and this leads to effective masses of electrons. And near conical points, this is a famous case that they think that they are massless fermions, like in graphene. Now, only now I get to the subject of the talk, unfortunately. Now, more about structure. Analytic properties of dispersion relation free and Fermi surface. First of all, as I mentioned, the edges of the spectrum occur where you have extrema, maxima or minima of dispersion relation. The conjecture is that for a generic operator of second order, generic in the sense that for almost every potential, let's say, those extrema are isolated and non-degenerate, in other words, parabolic. This is it's not proven. There are very few partial results, but everyone in physics and mathematics believes this. It's critical for many things. For instance, the notion of active masses assumes this. Green's function, asymptotics near the spectral edge is handled by this conjecture. Harmonization, Liouville theorems, Anderson, localization, etc., they based upon this. In discrete case, there are counterexamples. There are no counterexamples in continuous. It's believed to be true. And there are some cases when one can get positive results. Now, next thing is more, okay, I'm running out of time. Can I have a few more minutes?
Sure, you can go on a few minutes, yes. So you've still got another 10 minutes anyway.
Sorry?
You've still got 10 minutes.
Oh, okay. Oh, I forgot that I started at 6:10. Then I'm fine. something that seems to be much more esoteric. It is irreducibility of Bloch variety. What does it mean, irreducibility? Put it simply, it means the following, that if you take the dispersion relation and throw away all singularities and leave only smooth points, then it's connected set. In other words, what it means that if you know even a small patch of one band function, let's say, you know lambda 3 near a point, near a given quasimomentum, it uniquely determines the whole dispersion relation. That's a conjecture. So it's very rigid. You cannot do anything to lambda 3 without changing the whole dispersion relation. It is interesting property and in some senses important, but don't try to use it practically, since if I give you this small piece of lambda 3 and you try to recover the whole dispersion relation, you will fail in spite of the theorem, or even if this conjecture holds. Why? Since it means doing analytic continuation, which is numerically exponential and stable problem. This is proven, this is very hard to prove, proven only in 2D for Schrödinger operators with electric potential by Knörrer and Trubowitz. One simple corollary to show that it is related to anything is that it is much stronger statement than absence of bound states that you expect. Why? Since I will not have time to repeat the argument, but it's known that existence of bound state for such a periodic operator implies that for any quasi-momentum, this point k lambda is in dispersion relation. In other words, geometrically, you imagine that there is a plane, horizontal plane in the dispersion relation. And this is equivalent to existence of bound state. And since if such a plane exists, it definitely a separate component of dispersion relation. It knows nothing about the rest, and therefore it would have been reducible. So irreducibility is much stronger statement than absolute continuity. By the way, absolute continuity is not completely proven. It's proven for electric and magnetic Schrödinger operators, but if you enter periodic coefficients in higher order terms, it's still not proven. Now about Fermi surface. Can Fermi surface be reducible? Can it have several pieces that don't know about each other? Well, it looks even more esoteric, but it happens to be even more important. First of all, how can the Fermi surface be reducible? Imagine that you have direct sum of two operators that just don't know anything about each other. Then the Fermi surface will be just the union of their two Fermi surfaces, and they have no knowledge about each other. But so the question of reducibility of Fermi surface used to be considered very esoteric and not related to anything, till like 20 years ago, it was discovered that it is, there has been this old problem about absence of embedded eigenvalues. Namely, if you perturb your periodic operator by localized perturbation, we know that you can get additional impurity spectrum in gaps. There shouldn't be any inside of continuous spectrum. In 1D, this has been completely studied, and the result is that if the perturbation, starting this famous paper by von Neumann and Wigner, it completely resolved in 1D by Rofe-Beketov, that if perturbation decays sufficiently fast, essentially first moment is finite. Then you cannot embed eigenvalues. This thing was completely untouched for a long time in several variables. Why? And the reason is that this reducibility of Fermi surface is in charge. Namely, if you know that your Fermi surface at given lambda is irreducible, this means that if you add sufficiently fast decay and perturbation to your operator, impurity, it cannot embed bound state at this lambda. It's not if and only if. If it's reducible, I don't think it's true that you necessarily have a way to embed, but there are examples when Fermi surface is reducible and eigenvalues do embed. I can explain it as follows. What can happen that Fermi surface has component completely hidden in complex domain. You don't see it for real quasimomentum. And essentially, it is like having direct sum of two operators, one of which doesn't know about another. Therefore, it is allowed to put its spectrum, which in a gap for that operator, into continuous spectrum of another, since they don't know anything about it. It's not a theorem. I don't think there is a theorem like that reducibility leads to such split of operator, but that's the idea. Unfortunately, irreducibility for a continuous case is not well established. It's known in 2D for almost every lambda. And it's also known if you have, for instance, in 3D, completely separable potential or potential that separates into two variable and one variable potential. In discrete case, there are examples of reducibility, quite a few, including interesting cases of multi-layer graphene and other similar structures. And you could create embedded states. But there are also cases when you can prove irreducibility, some recent theory. Another thing about the geometry of dispersion relation. You know, this is a familiar picture from physics textbooks. That's a Brillouin zone. Actually, the true reduced Brillouin zone in this case is a triangle gamma x m gamma. And that's the picture you see drawn of the spectra. Dispersion relation is drawn along the perimeter of this triangle. First of all, it's easier to plot in 2D. And secondly, if you need to do actual calculations, it reduces dimension by 1, which is significant reduction. And there used to be widely spread belief that extrema, therefore spectral bands, spectral edges, have to occur only at those points that inherit some symmetries from your structure. And therefore, when you graph it only on the boundary, you have correct spectrum. It happens to be false. It's not true. It's not true. There are counterexamples even in 1D structures of waveguide types. So this is not true. And the last thing that I want to mention, people have worked a lot creating media that can freeze light, slow down light. How this can be done? You need to create a wave packet which almost doesn't move, that has very small, close to zero velocity. And how you can do this? It's known that the velocity of wave packet concentrated at certain quasimomentum is given by the gradient of dispersion relation. And therefore, if, for instance, you sit at the spectral gap edge, that's where you can try to create frozen light. I will not dwell on this. I just mentioned that the mechanism that is usually used both theoretically and practically is to create resonant gaps, which means that one of the ways to create spectral gaps is the following. You can spread throughout your medium small resonators. The same resonator is periodically placed. And one can show that then it will create spectral gaps, and they are useful for creating slow light. And that's all I want to say.
Well, let's thank Peter for a very informative and interesting panorama talk.